Hello everyone. Let us start the class today. Let us remind, in the last class we basically discussed the existence and uniqueness for the systems. Basically we are looking at the systems and we discussed the existence and uniqueness theorem for the systems. And the comment was that basically the proof are exactly the same as the case of first order scalar ODE, but you have to replace the absolute values with the appropriate norm. And once you do that, you basically get the exactly the same thing. So with that in mind, and then we discuss a little bit about the linear system, and in linear system we stated that if aij's, which are the coefficients, if they are continuous on I, so obviously they will be continuous and bounded, then we get a unique solution. Okay. Now, what I will do is that I will briefly recall what you have done in the first year, and I hope you have gone through the first year notes for your OD. So then we can go really fast and avoid some of the repetitions. So if you look at the linear systems, okay, and so the linear system will be basically written like x prime vector x prime is equal to a t of x plus some g. For the timing, let us avoid discussing this g. So we will have homogeneous system. So if g is 0, then we have homogeneous case. Okay, you know how to get from doing this doing this variation of parameter method, right, which guarantees you that in whatever your g is, you will always get a solution as long as g is an integrable function. Okay, so without going there, let us try to recall some of the interesting structure what you have for the homogeneous solution. So now there will be two discussions. One is about the homogeneous OD. Okay. And the second discussion will be about the corresponding initial value problem. Okay. So that means you will have some initial condition with some constant vector here. Okay. Now this problem, of course, will have infinitely many solutions. Okay, no matter the condition on A, and here if A the coefficient of this matrix A happens to be continuous on the interval, then what we'll have is basically unique solution. Okay, and then if you so what, but this infinitely many solution will be in a will form a basically a subspace. And what will be the dimension of that subspace? If A is n cross n matrix, then the dimension of the solution space is n. Okay, and this was proved in your first year lectures. Okay, so again a repetition. So let us assume that you have n linearly independent n vector functions. Okay, so you will have x 1 x 2 x 3 x1. So this is one vector function. The second vector function is x21 x2n. So the superscript represent the number and the subscript represent the component. So this is vector 1, this is vector 2, and this will be vector n. Okay. So now if you have these things, then what we did is, of course, you have to assume that they are defined from the interval I to R. Then we define something called Wronskian, and again this is already done for you, but I'm just repeating it so that you can recall it if you have not done so far. So the Wronskian of these n vectors, vector function, is going to be determinant. So let's write determinant explicitly. Will be basically x11, x12, and x1n, and similarly xn1 and xnn. Okay. And if Wronskian is at some t naught is not equal to 0 for any t naught in I, this implies that these vectors, so 1, xn, are linearly independent. Okay, again this is repetition, so there is no need of any discussion here. If please go through it. If you still have some doubts, we will be I'll be happy to discuss them. But this is there is no point for me to repeat the theory again and again. Okay, what is interesting is that you observe that there is something called Abel's formula. Again, this is from first year. Okay, so what is Abel's formula for the Wronskian? Can somebody tell me what is the Abel's formula for the Wronskian? Yes.
Into integration of e to the power integration of a of t dt, I think something like that.
Not exactly. So let me just give that thing and then you can recall it, because I'm not sure that you had like looked at the notes which I asked you. Okay. So let us assume that these are our n vector functions, and from they are defined on interval AB to R. Okay. And they are solutions. So to get the Abel formula, you need an additional condition that they have to be solution, and they are solutions of the system like this. Then the Wronskian at time t is going to be some constant multiple. In fact, you can take I'll come back to this constant again. Exponential integral trace of a. Now, note that a is a function of t, capital A, the component of a function of t. So this is also will be a function of t. So this trace has to be integrated with respect to that. Okay. So this will be the formula. Okay. Now, if you know the value of Wronskian at a point, then you can, this formula will be automatically modified. It will be Wt is equal to Wt naught exponential integral t naught to t trace of a s okay ds. Okay, so the fundamental fact is that if this value happens to be 0, then this value will be always be 0. Okay, and this will be always be non-zero if this value is non-zero. So if you find a point, if if these are solutions, but this happens only if these are solutions. If these are not solutions, then it can happen trace at some point is 0 and trace at some other point is not 0. Okay. But if there is solution, trace will either be 0 everywhere or nowhere it will be 0. sorry, the Wronskian will be 0 everywhere or nowhere it will be 0. This is what this Abel's theorem says. Okay, and with the help of this Wronskian discussion, you have general structure of the general solution of homogeneous problem. So how did you find the general solution? The general solution means that all the solutions. So idea was to find an linearly independent solution of the homogeneous problem. Okay, so once you find M linearly independent, so assume you have found them somehow. Linearly independent solutions of x prime is equal to ATX, then any solution, for any solution y of x prime is equal to ATX, there exists unique C1, Cn constants such that the vector y is going to be a unique linear combination of these solutions. Okay, and this was again proved to you in first year. So I'm just recalling that structure. And once you have that, you can of course go to the non-homogeneous case. Okay, by using variation of parameters. Or there are some other methods which is called, I think, you try to fix some coefficients and then, but that works only in certain cases. Okay, now I will not go into details of finding these, how do you find these n-linearly independent solution, but I will discuss the mathematical problem you face when you try to find them. But before we do that, let us also recall once I discuss systems, I have already discussed higher order equations. Linear ODE. Because any higher order linear ODE can be written into a system of ODE, a first order system of ODE, first order system, order linear system. So for example, if you take something like xn plus a n1 xn minus 1 and so on and so forth. So a1 x prime plus a naught x is equal to 0, or even if it's some gt. Here x is a scalar function from ab to r. Okay, then you can convert. So this is a linear ODE of order n. Okay, and then you can convert it into a system. How would you do that? You basically start writing by by defining a new vector component. So you basically say that y1 is equal to x, and y2 will be basically x prime, y3 will be basically x double prime, and so on and so forth. So yn will be basically xn minus 1 derivative. Okay, and then you can write y1 yn is equal to, now I will write it in system. So this again will be, so this is y1 prime, so this is y1 yn, okay, and now you can just fill the coefficient. So y1 prime will be basically x1 prime is y2, so this will be 0 1 0 0 0. So you will get 0 0 1 0 0 0 1 and so on and so forth, except the last row. In the last row you get yn prime, which is xn. This will be equal to basically these terms taken other side. So this will be minus minus a naught minus a1, and in the end here it will be minus a and minus 1. Okay, and of course then you have to take g 0 0 0 gt here. Okay, so why I'm doing it? Because then if you want to study the existence and uniqueness for this thing, you go back to the systems, you go back to this system. And not only that, all the properties of the system solution can be applied here, so that you don't need to bother about it. So what it means is that if these coefficients, they are not constant, of course they are functions of t. If they happens to be continuous, then we have a unique solution, because this is the statement about the system we use. Okay, so the higher order linear ODE will have a unique solution provided these coefficients are bounded and continuous on the interval. Okay, and similarly you can connect. Now what will be the Wronskian for linear higher order linear ODE? So the Wronskian, if you have solutions, let's say x1 x2 xn, so then the Wronskian in this case was x1 prime x nth component, and similarly here it was x n prime, and this is x n nth order derivative. So these are derivatives. Okay, now you can compare this with this Wronskian, and you see exactly the same thing. Only thing is that these indexes are switched. Okay, and so this is nothing but the corresponding change of variable. Okay, hence the Abel's theorem for this case is very straightforward. So Abel's theorem in this case will tells you that basically Wronskian at time t is basically Wronskian at time t naught exponential integral t naught to t. Now what is the trace here? Trace of a? Can somebody tell me what is the trace of a here? What is trace of a here? Just look at this one and tell me trace of a. Yes? No? Note that all the diagonal entries are zeros except the last one, and this is with the negative sign. So because I took this other way around, other side. Okay, so what you get is minus of a n minus 1 s ds. Okay, and this is this term, negative of this term. So I should write a here. So negative of this coefficient. Okay, so this thing comes only this thing comes. No other thing has any contribution. So you can see that again Wronskian will be either 0 everywhere or nowhere 0 if they are the solutions. In general, Wronskian can be 0 or not 0 at some other points if they're not, if we are talking about general function, but because they are the solutions, Abel's theorem holds. All right, and then again you can go to the method of variation of parameter for the systems, or and you can modify. You can basically get it for the higher order linear ODE. So there is absolutely no issue as such. Okay. So the method part is fairly simple and straightforward. What, however, I would like to discuss is something which is not done during the first year class, which is when you look at the linear system with constant coefficients. Okay. So that means I'm going to consider something like this, where A is constant matrix. Okay. And then you knew how to find the solution, right? You already know how to find the solution. There are three cases. Case 1, A has n distinct values, n distinct eigenvalue. In that case, the solution is trivial, more or less. So you wrote the first solution is basically exponential lambda 1, by assuming lambda 1 is the first eigenvalue, t the first eigenvector, let's call it v1. Okay, so let's call it v1. Similarly, x2, the second solution, was a lambda 2t, the second eigenvalue vector, and so on and so forth. So you got n linearly independent eigenvector. How would you prove that they are linearly independent? Can somebody tell me did you prove that they are linearly independent? How would you prove that these are n linearly independent solutions?
You can find the Wronskian.
Wronskian, okay, then?
Because the vectors are linearly independent, so that determines.
So you find the Wronskian at t equal to 0. Once you put t equal to 0, these terms will disappear, and what you left with these n vectors. And because they are eigenvectors corresponding to different eigenvalues, they will be linearly independent. Okay. So you get the situation. You get that they are linearly. In the case 2, you will have repeated eigenvalues, but you have you have complete set of eigenvectors, but we have n linearly independent eigenvectors. And in this case also it doesn't matter. It's exactly the case. In this case, you go back to this one because some of these lambdas might turn out to be equal to each other, but because these vectors are linearly independent, so there is no issue. Okay, so you will get exactly the same case. The case 3, and note that in both these cases, matrix A is what? Can somebody tell me what something about matrix A in both these cases? what happens in both these cases? Can somebody tell me what kind of matrix A will be?
Diagonalizable.
Yes, so matrix A is diagonalizable. Okay. So this is the most important part. Because of this, your life becomes easy, and we will see that why your life became very easy in this case. Okay. But in general, not all the matrices are diagonalizable. Okay, and then you did find some still, but you are still able to find some solution. So we'll try to understand what guarantees that you can find the solution in that case. Okay, that part was missing from your first year discussion, that what is the guarantee that even A is not diagonalizable, still you can find the solution. So before I go forward, let us recall what we actually did in that case. Okay, so let us look at the case 3. In this case, there is at least one eigenvalues. So there exists eigenvalue lambda such that geometric multiplicity is strictly less than algebraic multiplicity. So if you can find at least one eigenvalue for which this holds, then of course the matrix will not be. So the immediate consequences of this is that A is not diagonalizable. But still you went ahead and found a solution by putting some unsort functions. And let me explain how we did that. But there is a little bit more involvement here, because this is not just about method. It's also ask a natural mathematical question that why that kind of things exist actually. Okay, so before we go forward, let me try to recall what you did in this case. Okay. Okay. So let us assume now, because lambda is an eigenvalue, so I'm going to discuss only this case because other two cases are trivial, because you already know what is the eigenvalue. So in this case 3, what happens? So of course you will have immediately one linear independent solution. So because lambda is an eigenvalue, there exists at least one eigenvector, right? Okay, and what will be that eigenvector? So okay, before I go forward, in this case we are assuming all the eigenvalues are real. Okay, so this was the assumption. If they are complex, of course the other thing can be done, but that you already know. So so there exists at least one eigenvector. So this means you immediately have one solution in this case. This, let's call it x1. This will be E lambda t v1. One eigenvector, let's say v1. Okay, so one solution was more or less given to you. Then to find the second solution, you assume the second solution is of the following form. X2 is going to be basically v1, but you multiply it with E lambda 1 t plus, you to find the second one, so you write E lambda t u. Okay, where this u you need to find such that x2 is a solution. Obviously, once you find u2 vector which says that x2 is a solution, x1 and x2 will be linearly independent. Okay, because of this term, because this function and this are linearly independent. Okay, so now you went ahead and we go ahead and plug this one into our equation. So let us do that. So I want x2 prime to be equal to a x2. This is my requirement. Okay. Now what is x2 prime? So x2 prime is basically, so this side is equal to, okay, this side is equal to basically you have lambda t exponential lambda t. So I take derivative of this term, okay, plus exponential lambda t. Of course, everything is multiplied with respect to v1 plus sorry, there will be lambda no, the lambda is already taken care. Yeah, this is, there will be, then the next one will be lambda e lambda t, okay, u. So this is the right other side, and then a multiply with t e lambda t v1 plus e lambda t u. Okay, so this is the equality I want, and with this I will get a condition on u. Okay, so we use two facts. Here you will see immediately that okay, let's see one by one. Okay, so let us try to see from here itself. Now this a, so this is a scalar, it comes out. So a of v, and this is will be lambda of v. So this term and this term get cancelled because v1 is the v1 is the eigenvalue. Okay, so what you're left is this term, two terms this side and one term this side. Okay, so let us combine them together, and what we get is e lambda t, okay, v1. So this is this term plus lambda e lambda t u is equal to a e lambda t u. Okay, so now exponential is on the both sides, so I can get rid of exponential also. So let's just get rid of this exponential also. So what we get is a u minus lambda u, I took this one other side, is equal to v1. So I get a minus lambda I u is equal to v1. Okay, I did the whole calculation just to show you. Of course you remember it, and then you find this u1 u, and then if you still have one missing eigenvector, you went ahead and assume little bit bigger unsort functions and so on and so forth. But the question what we are currently concerned about is that what is the guarantee that such a U exist, okay, and most importantly this U should be such that this x1 and x2 should be linearly independent, right? It should not be that it's become a kind of useless discussion. All right, so what we'll try to understand now is that why such a U exists. What we are doing now is that because we have some missing eigenvalues, eigenvectors, we are trying to find a their replacement in such a way that we can find the solution of the ODE. Okay, so we are trying to find the missing eigenvectors. Of course, they won't be the eigenvectors. There will be something, but there will be something similar. How they will be similar? They will satisfy these kind of conditions. Okay, so now our next one class will be dedicated to basically explaining you how even when A is not diagonalizable, you can still solve the case. And then we'll combine the discussion in such a way that it will become for you, it will look to you very easy how you find all those unsolved solutions. So the mathematics story will be complete in a way that you will see that okay, it's very easy to imagine why those unsolved functions were used. Okay, so this was the missing part for you in the discussion we had. For example, if you have one more, let us recall that if you had one more missing thing, then what you did is that you took unsort function, something like t square by 2, some is the first function, the first vector v1 e lambda t v1 plus, let's say you find u here from here, so this is t e lambda tu, and then you propose another one e lambda tw, and w was again a minus lambda I w is equal to u. Okay, so this is just to recall, give you the just to recall what you did. So this is the typically the thing you did. Now we'll try to understand that why such a u or w exists, what is their relation with v1, and so on and so forth. Okay, any questions so far? Okay, so what we are going to look at is something called generalized eigenvectors. Okay, and of course once you do that, there will be something called Jordan form. Have you done another numerical analysis course other than the first year course?
No, sir.
Have you seen Jordan form? Have you seen discussion about Jordan form somewhere?
No, sir.
Okay. So this will be good thing in a way that it also covers a linear algebra topic in a sense that it tells you what you need to do if matrix is not diagonalizable. So what it will tell you that still you can be almost diagonalizable. Okay, so even when A is not diagonalizable, if you have real eigenvalues, you can still be almost diagonalizable. Okay, and this almost is the discussion about this Jordan form. Okay, now let us define something. So now we are discussing completely with linear algebra. So let A be n cross n matrix. Okay, then a non-trivial vector, a non-zero vector U that solves the system A minus lambda I K U is equal to 0. Of course, when K is equal to 1, then this becomes an eigenvalue, standard eigenvalue. Okay. So if K is bigger than 1, then it's called generalized eigenvalue. Okay. For some positive integer, K. Okay, so let A be a matrix, then a non-zero vector that solves the system for some positive integer K is called generalized eigenvector with index K. Okay, sorry, so not the index K. Okay, generalized eigenvector. Let us stop here. If K is smallest such integer, then it is called index of U. So of course, once it's true for K, it will always be true for K plus 1, K plus 2, K plus n, whatever it is, because it becomes a zero vector. So we take the smallest such thing such that U is a solution of this, and that will be the called index for the generalized eigenvector U. All right. Now, why I did that? Let us go back and see what we did. Note that if I apply A minus lambda I on V1, this becomes 0. So in this case, if I apply A minus lambda I this side, so what you get is that A lambda minus I square applied on U is a 0. So U is a generalized eigenvector with index 2. Okay. Similarly here, you can see that W will be generalized eigenvector with index 3. Okay. So these what U and W, what you found here to put here, they were the generalized eigenvectors. What we'll show you here is that what is the effect of these generalized vectors on the matrix A, and how easy it make A look. It makes A almost diagonalizable. These vectors make A almost diagonalizable. Okay. So now let us continue this discussion. Let us, for K equal to 1, of course, U is just an eigenvector. Huh? Okay. Now we defined, if K is not equal to 1, then we define a sequence. Okay. We define a sequence something like in an inverse way, something like this. Okay. And this this, if of course I need to say that U Vk equal to Uk U. Okay, so because I choose U, or yeah, okay, for k not equal to 1. Okay, where vk okay, for k not equal to 1, and I need to be careful here because I need to show that vk is the generalized eigenvector with index k. So if vk is the generalized eigenvectors with index k, then let us look at this one. This will be a generalized eigenvector with index k minus 1. And so on and so forth till you reach v1. A minus lambda I k minus 1 vk. Now this v1 will be an eigenvalue. Okay, is this discussion clear? Is this discussion clear so far?
So how this V1 is an eigenvector?
Sorry, ask
How
again.
this V1 is an eigenvector?
Oh, it's very simple. First thing you have to note that this is not 0. Okay, and second thing is that if you note that is not 0, then you just multiply a minus lambda I over v1. This will be a minus lambda I power k of vk, but this is equal to 0. So it's eigenvector. Okay. So basically, this is the eigenvector. This is generalized eigenvector of degree k. Every time you multiply it with 1, you get a generalized eigenvector of 1 lower degree. You keep decreasing this index, one less index. You keep decreasing this index. At some point of time, it will reach index 1. And index 1 means that it's an eigenvector. Okay. So if its index to start with is k, you multiply with this k minus 1. This makes it eigenvector. Okay.
Okay, so the UKs are these UKs are the generalized eigenvectors.
So here what I'm doing is that I'm constructing an eigenvector using a generalized eigenvector.
Okay, sir. Okay.
Okay. What you did in the solving the ODE, other way around. And this is, you can see here also, right? From this you went here, from here you went there and there and there till you had all the missing eigenvectors. Okay. But we are not doing that here. We are doing it some other way. Because we are trying to understand what is the relation between them and trying to develop a corresponding theory. Okay. So in the next class, we'll discuss the relation between this and this vector and how to find such a vector and how they are linearly independent. And then finally, our aim is to write A into almost diagonalizable form. Once we do that, then we look at a kind of whole linear system with constant coefficient in a different way. And I will show you that it's very easy if you are comfortable with that way. You don't currently you have to do a lot of process to see it, but once you do look at it that way, it becomes very easy to see those solutions, what the unsolved solution, what we discussed, these kind of things. they becomes very natural that way. Okay, so that we'll do in tomorrow's class. Tomorrow we have class. Okay, so I stop the recording and then we can I'm here